you guys, it's very difficult. So please, you guys, please try to follow me and try to understand. I'd like you have a basic impression of this part. So the whole chapter here, we are talking about principle of angular momentum. This principle is try to give a clear relationship between uh, external forces, its movement to a fixed point or a mass center, and the motion of the body or body system it have. No? So that is the principle of angular momentum. Actually, through the chapter 12, maybe you guess you have some tiny impression, I think. We talk about principle of momentum. Actually, that principle gave us a clear relationship between force and motion. That is linear acceleration. We have mac equals sigma f, right? This is the most difficult chapter for me. Yes, I think it's quite difficult. It's quite difficult to understand. But I think you just try to follow me. I will do my best, try to explain to you guys. Um, although the process or the proof process is very difficult for you guys to understand, but I hope you guys can know how to use this kind of principle to tackle some typical simple example, right? If you still cannot understand the typical or simple example, that's okay. That's okay. I only need you guys have a basic impression and don't worry about the final examination of our course. I will give you guys open paper and give you guys enough time to finish that paper, and almost all the questions you will find the answer from this textbook. Okay, so please try to follow me, try to understand the more you can, the best you can. Okay, okay. So don't worry about the final examination. So actually, you guess attendance is very important. I think in most of the time, there are only 10 to 11 students come to into our classroom. Maybe some gentleman never showed up. I don't know who is that guy who is never showed up, but clearly your attendance will in somehow, I think it will uh, decide your final result, right? I think it's fair enough. So the more time your attendance, maybe the higher your final marks will be, right? Of course, it also according to your answer of our final examination, right? So let's back to the topic of today. We're trying to talk about the principle of angular momentum for a system about mass center. So mass center is a very special and very important center or point of a body or body system, right? So actually, we have a very famous formula. Actually, we better remember what it is, but I think maybe it's difficult for you guys. Actually, it's difficult for me to write something on this screen because it's hard to just use mouse to write something. Let's see, this is the position vector of our mass center. It rely on or depend on our reference coordinate system. But you guys can think that if we give a fixed coordinate system first, then we can use expression to find its position vector at that reference coordinate system, right? So let's say uh, each we have a lot of particles. Each particle has a mass mi, and each particle have its own center, and that centers that's this is r, difficult to write. That centers vector position is ri right? And over sigma mi. So actually, we use this formula all the time. It's very important. Next time, maybe I will teach you guys another course, engineering mechanics second, right? So you guys can think about that. I can remember. Maybe we will reuse this expression. So here, I just to mention that this mass center is very important. It's very special. So as described in equation 13 to 15, we will not back to that expression. The angular momentum of plane motion of a raised body about a fixed point O, that's LO, the angular momentum about a fixed point O, we use this LO to denote that. And there is a clearly relationship between the angular momentum about a fixed point O and about the mass center C. So we have this LO over the equal LC plus RC cross product MVC. So actually here MVC is the momentum of this body about because we see the absolute velocity of its mass center, right? So MVC actually the momentum. RC cross product MVC actually is more like if because this MVC is another vector, a force is a vector. So if we have RC cross product F, that means this F, this force F is moment, right? It's moment to point O, right? So here means the angular momentum of this momentum MVC to the point O. So that is the relationship between LO and LC. So because we have learned the principle of angular momentum for a system about a fixed point, so here we are going to give another principle that is about the mass center. So you guys just follow me, just to have a basic impression here. So that's true. It's a relationship between these two guys. So we can write it as because LC means the angular momentum of a body about its mass center. So actually this one equal GCZ prime times omega. Omega is angular velocity. GCZ prime actually is mass moment inertia. Do you guys still remember? I hope you guys can remember some simple shape is moment, mass moment of inertia. Mass moment inertia. Let's see. Let us review that together again. So if we have a thin long bar, which is homogeneous, right? They have length L. It has a mass m. So if we talk about its rotation around the fixed axis about one of its end, maybe this end, maybe this end, then its moment, the mass moment inertia will be gz equal 1/3 m l squared, right? And if just find its mass center, which is very simple to find because just at the position of half L. So we will have its GC always will be 1/12 m squared. So can you guys tell me if there's some simple ways to read this 1/12? In Chinese, I can say that 12/1. That means denominator is 1 and the denominator is 12, and this is a fraction. But I don't know exactly how to read this in English. So in many cases, I just read that about 1/12, or 1 divided by 12. I think it's not the best way, but I don't know how to read it clearly. If you guys know how to read that, you can tell me. Thank you very much. So this is GZ is 1/3 L ml squared. And about its mass center will be GC is 1/12 ml squared, right? So this is the number one simple shape of body. You should know it's two mass moment inertia, right? Another is if we have a disk, no, here it is center O. So if we have another homogeneous disk with R in its radius and its mass is M, so we will know its mass moment inertia about O. GO will be half M R squared. So if we have another circular shaped body, but it tells us that almost all the mass are distributed on the on this brim, maybe 边缘, right? So it's more like a donut because the internal one had no mass. So this kind of shaped disk is also have a center O, but all the mass are distributed along this outermost circle, right? So this GO will be just M R squared. So that's the basic things you guys should remember if we encounter that in some example, maybe in some body system, there somebody is this linkage of this disk or this maybe. So you guys should know this. If you guys cannot remember that, but when I talk about this, you should know, right? You should know. So back to here. So we have this LO equal LC plus RC cross product MVC, LC equal GCZ prime omega. And this MVC times D, because here we are talking about plane motion. So its computation is very simple. Just need MVC times D. Actually, this D is the two axis is distance, right? So if we have two axes, one is through this O, another is through this mass center C, these two axes are parallel. Their distance will be D, right? So when applying what we have learned the last time, applying the principle of angular momentum of a system of particles about a fixed point. So that is this. So that is this. This is what we have learned. No, this dLO dt should equal sigma MOF. That is all the external forces is moment. It is geometric sum of moment about the same point O will just equal to the derivative of LO, right? So we just replace this LO with this. So that means D RC cross products MVC actually sigma MI, that is M, right? The whole mass of the system of particles. VC is the absolute velocity of its mass center of this system of particles, right? So just like this should equal this because sigma MOF can also written as this, right? You just consider all the external forces is a moment to the point O, and all this moment is a geometric sum will be this. So this one just is equal, this one is equivalent, and this part will equivalent to this part. So first, we just consider the left side of this equation. So maybe you guys will find it's difficult, but it's definitely true, you know. So if we do the derivative calculation, so first we'll consider the first part because there are two atoms, RC cross product this atom. So when we do the derivative calculation, we should just do drc dt and cross products the whole left part will keep its original pattern. So it just is drc dt cross products this, and plus this time we will keep this rc never change and cross product this. So this one, so this time we will just keep this. We will keep this, don't change, and we will consider d mvc dt. So here actually we just it's equivalent to sigma mi dvc dt here, and then this part of it just write add dlc dt. Then we will try to simplify this. So because from the middle part of this course, kinematics, right? We know the position vector of mass center RC, drc dt will be the absolute velocity of mass center C. So that is VC. So we will have the first part of this one will change into VC cross product MVC. So because this vector actually is parallel to this vector, then the cross product its result will just be 0. Because from the mathematical knowledge point, you guys should know actually two vector cross product its magnitude will equal this norm VC times this norm MVC times the sine intersection angle between this vector and this vector. Because these two vectors are parallel to each other, so the intersect angle will be 0 and the sine 0 will be 0. So the whole result will be 0. So that means this part can be eliminated because it is 0 result. So just erase here. We do not need to consider this part anymore. And about this part, so do you guys still remember actually this is what we have learned from chapter 12. So dvc dt actually is what? Actually is MAC, that is absolute acceleration of mass center C. So it's just simply in simple change into RC cross product RC cross product MAC sigma mi actually the whole mass of this system of particles. So that is this. And another one I will change the original this. So just replace the same one here, dlc dt. Then we eliminate this part and change into just the two parts left. So the first is RC cross product MAC plus dlc dt, right? And this time we are going to consider about the right side of this equation, right? So here the Ri is we arbitrarily select a particle from this system of particles, and Ri is position vector. So this is external forces Fi, which is exerting on this particle, and we just consider this force is moment to the fixed point O, right? So, but this time we will use Ri actually equal Rc plus Rri. Do you guys still remember? Actually, we have another coordinate system, so which is origin point at point C, and we have x prime, y prime, z prime. It's never changed its orientation. It's just move along the body. But when the body has some rotation around this mass center C, this moving coordinate system will never change its orientation. So actually, Ri is the position of that particle above the fixed coordinate system, and RC actually is our moving coordinate system. Is position vector, and RRI actually the same particle is relevant. It's relevant relative to the moving coordinate system is a position vector. So I hope you guys can understand what I'm talking about. Actually, I come back to the part we have learned. Actually, we have that kind of I think we have that kind of uh, figure here. So you guys, you can look at this figure 13 to third. Actually, this is our fixed coordinate system, O, X, Y, Z. Let's say this is a system of particles, and this C is mass center. So we can deliberate to build another moving coordinate system, which is C, X prime, Y prime, Z prime. Because this C is this new building new coordinate system origin point. And the second is this Cx prime, Y prime, Z prime will just move along this body. When this body have rotation around the point C, this this coordinate system will never do that. That means it's just move along with this body, but it's never rotate with this body. So you guys can hear if this is y, Ri equal Rc plus Rri, right? It is the same particle we just select to denote to you guys. That relationship will always be true. For any arbitrarily selected point or selected particle on the body, we always have this relationship, right? So if you can understand that relationship, then we come back to here, try to understand that. So we just use RC plus RRI equal RI. Then we have this. So we try to do the simplification. So this will be changed sigma RC cross products FIE plus sigma RRI cross products FIE, right? And this part, we just change this into, because RC for any particle, RC will never change its magnitude and direction, because RC is the mass center. Mass center C is position vector, right? So it's independent to any individual particles. So we can just write as RC cross product this. But why we write the sigma FIE? So maybe I will. So this part, it can write as or we I can say it equivalent to RC, cross product sigma FIE. But do you guys familiar with this part? Actually, we have learned from chapter 12. We have we have MAC equal sigma FIE. Actually, we have used this expression to tackle a lot of examples. Actually, this is the principle of momentum for a system about the mass center. 质心运动定理. We have learned that. So actually, sigma FIE just equivalent to the whole mass of the system, and times the absolute acceleration of its mass center. So this guy can be rewritten as this. So why should we do this? Because we can find this the right side of the equation up here, and here we have this the same part at the left side of this equation, and we keep this, don't change. So you guys can find, because left side equal right side, right? So we can once again eliminate this, right? This part and this part will be eliminated. Then we have the final result. So the principle of angular momentum for a system about the mass center is dLc dt equal sigma mcf. Actually, it is, it is GZC one. GZC 10, because, here we have GCZ, right? Omega, its derivative will be alpha, that is angular acceleration. It will equal what? Equal sigma mc FIE. It's hard to read, so please you get maybe you should write at this to denote that all the external forces. So this equation states that the time derivative, I don't know, time derivative. I don't feel familiar with this letter, this word. So the derivative calculation about LC, that is dLc dt, of the angular momentum about the center of mass is equal to the moment of all the external forces about the same point. See, that is another relationship. And this principle is the key that we can give the function about a body which have a plane motion. We can clearly give the relationship between its motion and all the external forces acting on the same body. That's very important. So maybe I should repeat that again. The derivative calculation of LC, which is angular momentum about mass center C, will equal to the moment of all the external forces about the same point C. The same point is the mass center C, right? This is the principle of angular momentum of a system with respect to center of mass. The equation is well known, and the principle of angular momentum with respect to the center of mass. I think it's very complicated to just express this principle in English. So actually in China, we will just call that 动量矩定理，关于质心的动量矩定理。The principle of angular momentum about the center of mass. So the change of the angular momentum of a system of particles with respect to the center of mass only involves the external forces acting on the system, not the internal forces. Why? The reason I have mentioned many times, because all the internal forces will constitute a lot of pairs of action and reaction forces. So for a pair of action and reaction forces, they always have same magnitude, opposite direction, and collinear. So their moment to the same point, its sum will always zero. So we do not need to consider that. So that means internal forces cannot change the momentum and the angular momentum of the whole system, right? So if we finally have this result, although this process of proof is very difficult to understand, but you should know we always should use this principle to tackle some example. So let's see the first example here. Let's see the first example. The bar OA, the bar OA has a mass of M and length of L. Do you guys still remember what we have reviewed here today? No? LM. So you should immediately think about that. If GZ should be this, if GC should be this. we should remember that just like we know the gravity acceleration of the Earth is 9.8 or 10, right? So it should be a common sense. We should know that immediately, just like we know 1 + 1 = 2, more like that. So the bar OA shown in figure 13 to 16 had the mass m, length L, and its initial angle with the vertical direction is. So we have a vertical line here, and its initial position is here, OA. You know, OA should be here. OA have intersect angle with the vertical line with theta, right? Disk B had the radius r, mass of m, and the initial angular velocity is omega 0. I think here it means we are sitting on the OA. We look at this disk. It will have a CCW direction, angular velocity, omega 0, right? So that is the real meaning. So B is joint connected to OA. That is from the first part of statics we have learned of this course. The first few weeks we have learned that. So that is very common constraint, right? So it joint connected with OA. Question is, what is the motion for disk B after releasing it from rest? That means at this position, OA is rest at this position, but B has its own angular velocity omega 0. And when we do not control this OA at here, that's just is we release it from this position. What about the motion for disk B? So you guys please see the solution and try to understand. So we just select this disk B to be an object to be investigated. So we just give it force analysis because it has mass m. So it will have gravitational gravity, right? Mg, because of the contractile force because of the Earth, mg. We trying to call that 重力, right? 重力, gravitational force. And then because this is kind of pin, right? So it will have two kind of forces, which is Fax and Fay. So that is force analysis. We can call that FBD. It's free body diagram. And we also can do its motion analysis. So at this initial position, this disk B has angular velocity omega 0, right? With this direction. So that is MBD. We can call that motion body diagram. It's motion analysis. So this is then we should use what? We should use this, what we have learned, you know? This A actually is the mass center of this disk. See? This A actually is the mass center of this disk B. So we can just write its angular momentum about its mass center. We just write as LA, right? So LA actually equals this. Do you guys know? For this disk, actually JB have 1 mr squared. No, it should be equal this. It tells us it have r and the mass of m, and omega b just in the any position. We just write as omega b, right? It always should equal what? Should equal sigma MAF. But believe you guys, do you still remember what about the force is moment to an axis? So because Fay FAX and MG, all the three forces, their action line are intersect with the axis, which is perpendicular to this plane into the screen. So that means sigma MAF will always be 0, because when one force it have intersect and point with the axis or parallel to that axis, the moment these two conditions, just one of the conditions is fulfilled, its moment to this axis will be 0. So here, for this case, at any position, maybe because you tell us it's a released at this position, so because of the gravitational force, it will swing along this direction, right? This is common sense. But at this process of movement, we can find for disk B, all the three forces, there are no any other type of external forces. So we already have sigma MAF equals 0. So that means because the principle of this dLA dt will equal this, will equal 0. That means LA will be what? Will be a constant vector. Because at the initial position it equal GB times omega 0, and GB will never change. So that means, so therefore omega B will equal omega 0. Why? Because GB omega B will be a constant vector, right? Because GB times omega B dots, that is alpha B, will be 0. So this guy must be a constant vector because at the initial position, we have omega 0. So it will equal JB omega 0. No, that's why the result is therefore omega B always equal omega 0, which means what? Which means the angular velocity of disk B will be a constant, you know? So maybe it will fall from this position to this position, but its CCW rotation about A will never change. Will never change because there are no external forces will have a direct influence to that rotation. So once again, the moving of mass of center and the rotation about the mass center is just two independent movements. They will influence no to each other. You know, they are independent. So once again, if this disk B actually have a plane motion, right? It will move along this OA because this OA will swing from this position to this position. And also at the same time, this disk B also have a rotation around the point A. So this is a typical plane motion of disk B. So since the two motion components are totally independent, so that's why we can use a motion superposition. Do you guys still remember what we have, what I have mentioned that I think many times? Motion superposition. It's hard to write this. Superposition. Superposition. Actually, that is the principle of us how to analyze the complicated motion superposition TION, right? Since these two motion components are independent to each other and they are happening at the same time, so we can imaginary think about that the two motion component are happened successively, not simultaneously. Can you guys hear me together? Hear me clearly? That the principle of motion superposition. I'll show you guys how to use this Chinese to describe this principle. 运动叠加原理. Because when we use this, we can very easily understand the complicated motion of a body it has. So because these two components is totally different, we can think that this disc first is don't rotate about A. It's just move along this OA from this position to this position. Then it will stop at this position. Then its own rotation will happen. That is what I say. These two independent motion components are happened successively, one after another. So this time you will find actually that two components are very clear, which the first one is translational movement. Another is just the rotation about fixed axis, right? So we also have the second method. So first we think this OA stayed at here. Then the disk B first finish its rotation about point A. So maybe because of the total time will be a t, then it will rotate about some angle from one position, rotate to another position. Then it stopped rotation. Then it will just move along this OA from this position to another position. So that also a two independent motion component happened successively. So you guys can find this method will help us to analyze this complicated movement or complicated motion more clearly, more easily to understand, right? So that is the principle of motion superposition, 运动叠加原理. So I hope you guys can understand that more. So if we know this result, DLC dt equal sigma MCF, then we once again talk about the conservation principle, 守恒定律, right? It's easy to understand. So conservation principle of the total angular momentum of a system. So that means, so from the equation, 13 to 19, 13 to 12 to 21. Here, 13 to 21, or 13 to 19, where is the dLO dt. So that's the same case, If MO equals 0, that means dLO dt have to be 0. So just more like what we have discussed this simple example, right? So here actually is the can of conservation, right? So if external forces is geometric sum of moment to fixed point O is 0, that means dLO dt have to be 0, right? So that means LO will be constant vector. We call this result is the can of what? Is the can of 守恒, the can of 守恒.守恒 means 不变, right? Means never change. Because LO will be a vector, it has direction and magnitude. So if this condition is fulfilled, then dLO dt have to be 0, then we can see this vector of LO will never change. That means its magnitude and the direction will never change. So it will be a constant, right? Constant vector. So at the initial position, if LO equals 0, then it will be R will be 0. So you guys can find this the 12th and 3rd atom. Actually, I think it's very easy to understand. If MVE, that means the external forces its geometric moment about a special axis. Let's see its name is z is 0. That means LZ will be constant. That means the angular momentum about this axis of this system will never change. Again, if mcz equals 0, that means for a body, if all the external forces acting on this body, their geometric sum of their moment to the mass center C is 0. That means, LCZ must be constant vector. So I can write for you guys again. So actually XC we can write as MVC. Right? It will be constant. Will be constant. So actually the best or important is if we also have another condition that at the initial position the whole system is rest. That means LC will equal MVC equal C will equal 0. Right? Then we will have, because dVC equal drc dt. Right? drc dt. So this guy is 0 and this guy will be 0. Then we will once again have our position vector of mass center C will be constant. See? You still remember what we have learned example about a person which is walk from a ship from the left side to the right side. And if we have a body move from a slope from the hair position to the bottom position, and the bigger one will back to left a little bit, that is the conservative of the momentum at x direction. That is px will always be 0. So it is the same reason. It is the same reason. So you guys can try to understand. So we will stop here. Let us to have a short break about 10 minutes. We'll restart at 11:10. Okay?
Okay.
So please, you
Okay,
guys
Alex.
have a short break. Okay, guys, let's see another example. Actually, we just finished to talk about the conservation principle of total angular momentum of a system. So here total, I think it means for DLO dt equal sigma MOF is true. For DLC dt equal sigma MCF is also true. That's why here we have a total. That for all the angular momentum for a system, we always have this conservation principle. Actually, we have talked about this kind of conservation principle at last chapter 12, right? So let's say together this example 13 to 10. Maybe I should cut this figure for you guys. It easy for us to talk about. So I will cut here and I will open it. See? So actually this example is a little bit interesting. You see? So let me introduce to you guys. Let's see together. So the mass of two monkeys, we have a big pulley here. Its mass center is O, it has radius R, and we have the string, right? So the left side call that A, the right side call that B. So actually we have two monkeys. Do you guys think that like a monkey? I don't think so, right? So it has the mass of two monkeys A and B are MA and MB, right? So we have MA equal MB. So monkey B clamps up upward, monkey B clamps upward with the relative V relative, that's very important. That means this monkey B has a relative movement to the rope from rest. So the initial condition is that two monkeys maybe just stay here. It's in a state of equilibrium. But from the time start, maybe this monkey will have a relative movement, have a relative velocity v upward to climb this rope. Then this monkey also have a movement, right? So it tells us to determine the motion of monkey A moves when monkey B climbs upward. See, we have a big pulley here. We have monkey A and B, and we know monkey B have a relative velocity upward. So how do we tackle this problem? Let's see the second question. The velocity of monkey A, we're just neglecting the weight of the rope. So how should be this? Let's see the solution. So the moment of all the external forces about point O is what? So how should you guys understand this result? It tells us the moment of all the external forces about the point. That means, let me explain to you guys, that is, we select this whole system to be an object to study. So actually, we can know the external forces including this MAG, right? MAG is gravitational force. Another is this MBG. It did not tell us, but I can assume that the weight of the pulley will be P, right? And here is the pin, so it will have constraint forces FOX, right? FOX and F(y). That we give is FBD. We call that free body diagram. We get all the force analysis. So you guys can find this force analysis. So we have MAG, this mancate gravitational force, and this MBG to denote this mancate gravitational force. We have gravitational force of the whole pulley with P and FOX, FOY. Then we are going to consider its sigma MOF, right? We are going to consider the sigma MOF. I think that is all the external forces, their moment to the same point O, we should find the geometrical sum. So actually FOY, FOX, and P, more like the first example we have talked about here, right? These three forces have zero moment to the point O or axis O. So we only have this. Then let's see, this MAG, it will have a moment to this point O with CCW direction. Let's see, that is positive. So we have MAG times arm length, moment arm length, right? Times R. And we also have these external forces, MBG, also downward direction. But this force, its moment to point O, will along CW direction, that is clockwise direction, because we give this CCW is positive, then its opposite direction will be negative. So we have to minus MB GR, right? So from the condition we have this MA equal MB. So you guys can find, since MA equal MB, so here we will have, it will be 0. That's why you tell us the moment of all the external forces about the point O is sigma MOF equals 0. That means it will be what? Conservation principle will be applied. So if we try to write LO, so here is a very important thing you guys should remember, should pay attention to it. When we talk about momentum or angular momentum, when we use this velocity, we always means absolute velocity. So let's see, after the force analysis, let us try to write LO. We should assume that this mancate, because it just grasp this rope, it has no relative movement with relative to the rope, right? It moves with the rope because the mancate upward relative to the rope. Then this mancate have to move. Why? Because it should keep the system, its LO will never change, right? Because at the initial, the system is rest, right? It's rest. So LO always be 0, right? If we assume that its absolute velocity VA is here upward, let's assume absolute velocity of mancate B with VB also upward. So we will have, because MAVA, MAVA is angular momentum to point O will be MAVA times R. So if we write here, this part is positive, means we just assume the angular momentum with CW direction is positive. See, this positive direction is totally according to us. You can select or you can arbitrarily select one. Maybe some gentlemen from our class tell me, Teacher Fang, actually I'd like CCW direction will be positive. Okay, that's okay. So here MAVA, this is the direction of its momentum. So its angular momentum to point O will be MAVA times R. It's along CW direction. So here we just assume that this direction is positive. Then when we back to here, we have MBVB, but you will find MBVB in angular momentum to same point O will be CCW direction, right? Will be CCW direction. So we will have to give a negative sign. MAVAR minus MBVBR. Actually, MA equal MB, R equal R. So we will have this expression. That means the absolute velocity of monkey A and monkey B will always be equal. So if at the first time at the initial VB is 0, then VA will be 0. So here we are talking about what VB is when the monkey have a relative velocity to the rope. So actually, can you guys still remember what we have talked about the composition of absolute velocity, relative velocity, and transport velocity? So maybe I will write here again. Maybe you guys have, maybe you don't have any idea. Actually, we have learned that. I will write here. Can you guys have some impression? VA means absolute velocity equal VE. When we were learning that, we call that transport velocity. And VR means relative velocity. So back to here, we are trying to find the absolute velocity of monkey B. So we just use VB to denote its absolute velocity of monkey B. So it should equal transport velocity, that is the velocity of the rope, right? And the relative velocity we have known, it have a relative velocity v relative to the rope. So actually here our VR will be v. It's upward direction. And actually when VA move like this, so that the transport velocity, if we talk about the moving point, moving point is monkey B. So the MCS moving coordinate system will the rope, will the rope. So if we assume that monkey A is grasp this rope, have absolute velocity upward, so upward, but then the right part of this rope will downward, right? It has the same magnitude with VA, but it will, because this part red and this part of rope will be false, right? So here for monkey B is transport velocity will be minus VA. So that's why we have V minus VA, right? So it's just right as this is very confusing. We cannot find why it is this. Actually, I think we should VB equal V minus VA. Then we rearrange this expression. We will have VA equal V minus VB. So if we directly try to understand this expression, it's very confusing. Why VA equal V minus VB, right? So if we have this condition, then we can write as VA will equal VB and also have equal, because VB equal V minus VA, right? Minus VA. So we will find actually VA will equal half V, right? Then the absolute velocity of monkey B also is half V. See, although this figure is very simple, actually this example, including a lot of knowledge points we have learned from the kinematic part and the dynamic part. See, can you guess? Totally understand why this solution is. Although there are a few lines, but actually it includes a lot of informations, right? So since we finished this section, the second section is learning, we are moving to the new section. So the third section of chapter 13 talk about differential equations of motion of a rigid body. So if you guys have a deep learning or deep understanding of the second section up here, we talk about the principle of angular momentum, about a fixed point O, or about a mass center C, then this section maybe is very easy to understand. So let's see. I will try my best to explain to you guys. So first, we'll talk about a rigid body which have a plane motion. So in many cases, in our examples, in our engineering life, the most case is our body will have plane motion. So the free body diagram, you see, we call that FBD, means free body diagram. So in a free FBD, we just give the force analysis. Let's see, we just use this arbitrary shape to denote a rigid body. And let's see, there are a lot of external forces F1, F2, and F3 acting on different points on the rigid body. And let's see, this C means it's mass center, and about a fixed coordinate system is position vector is R here, right? So let's see. The diagrams actually display the cross section of a body that is parallel to the plane motion. Actually, we have explained the reason when we analysis do the analysis of a plane motion. We just need a plane figure is enough. You know, do you guys still remember? Actually, we have learned this. So if we find a section, so if this body have a plane motion, then when we draw a lot of vertical line, right? We will find all the vertical line will have translational motion, right? So for a single line, we just need one point to denote all the other point, which is on the same line of the body. That means this point will denote a lot of points on the body, right? If we draw enough number of vertical line, we will see all the lines will have the according intersection point on the section, and all these points will constitute this section figure. That means it will denote all the moment of any point on the body, right? That's why we just need to use this cross section that is parallel to the plane motion and contain the mass center C of body. So to obtain the two-dimensional formulation of the plane motion, we assume external forces F1, F2, and a lot of other forces lying in the plane of the cross section. You know, and the cross section is the plane of symmetry of the body. This condition is very easy to fulfill, right? We need to use this section to be a reference section, and the up part and bottom part will be symmetrical about this section. It's easy, right? It's easy to manufacture this kind of body, right? So we can simplify the plane motion. We just need to study like this. And then in plane motion, the angular momentum of body about C, you know, we have the angular moment about matter C is given like this, right? LC equal GC omega. GC means it's mass moment inertia. we reviewed many times some simple shape of body is mass moment inertia, where omega is the angular velocity of the body and gc is the mass moment of inertia, right? About its mass center c. Hence, the resultant moment of all external forces about c. So can you guys understand this sentence? What is the resultant moment of all external forces about C? Actually, we have a method. We can simplify all the force into this mass center C. So we will have a principal force Fr, right? And a principal moment MC. So actually for plane motion, that because the Fr, it will cost that this body will along the direction of Fr have some linear acceleration. That is, we will have MR MA equal Fr, right? That's what we have learned, the principle of momentum from chapter 12, right? Because this vector equation can be projected onto x-axis and y-axis. Another is this, right? From the principle of angular momentum about mass center C, we do the derivative calculation. We will have gc alpha, you know, gc alpha is rotation angular acceleration to the equal what? Sigma mcf, right? That is, if we do the simplify all the external forces onto the mass center C, we will have a principal force Fr. We call that 主使 in Chinese, 主句 MC in Chinese, principal moment. So actually, because MC not zero, so we have GC alpha equal this. If Fr is not zero, then we have MA equal 0. So let's say we have the condition. If when we do the simplification, and we finally find it's very very how to say 巧合 coincidence. Fr equals 0, MC equals 0. So do you guys remember if we have the condition fulfilled, we found Fr equals 0 and MC also equals 0. What that mean? What that mean? That means the body is in the state of equilibrium. Actually, these the three equations from the first part, what we have learned, statics. Because statics just study the body or body system in the state of equilibrium. Then we can find the relationship of all the forces, right? So you can find, actually, when we talk about equilibrium, means A equals 0 and alpha equals 0, right? It will just rest or have a linear uniform translational movement. So until here, actually, all the things we have learned, we can just use these two equations to denote that, right? So the middle part, what is kinematics, just tell us how to find the information of a body or body system. Is displacement, its velocity, and its acceleration, right? Maybe linear, maybe angular, maybe translational, maybe rotational, right? So hence the resultant moment of all external forces above C is sigma MCF. And the resultant force is sigma Fi, sigma Fi actually the principal forces and principal moments. Applying the theorem of motion of center of mass, that's what I have right here. 质心运动定理, we have ma, that is d from d squared r dt squared, right? Actually, this is acceleration a, right? So we have this, here is ax, here is ay. And then applying the principle of angular momentum, we have learned from equation 13 to 19 and equation 13 to 12, 21. We can get another equation of gc theta double dot actually the angular acceleration, right? 角加速度. So maybe gc theta 2 dot. Or if we have a rotation around the fixed point, we can just select that point A. It's very simple. So we also have GA theta double dot equal this. So that's the differential equations of motion of a raised body. So since we have subtitle is plane motion, so from here we can think about that actually out of the three types of motion of a raised body, it can of plane motion. Let's say if we talk about a body have a translational movement, translational, it don't have rotational component, translational, that means it only need this or these two equations is enough because its alpha will always be 0, right? So if we talk about the second, if a body have a rotation around the fixed point or fixed axis A, we just use these two equations plus this one, right? So this will give the relationship between external forces is reductant sigma fi and is acceleration along x or y. And this equation will give the relationship between angular acceleration and external forces at the moment to the same axis or point. See? So that the second is rotation around the fixed point or fixed axis, right? And the third is the plane motion. That is, it has, because if a body only have rotation, not have translation, that means it only have this. But we still have these two equations. Let me give you a detailed explanation. So maybe you guys can have a deep understanding. Let's say again. So let's say we have a thin long bar which rotate around point A. Let's say its bar is AB and it have this omega or alpha and omega. So you guys will see since it only, let's say its mass is m, its length is l, right? You guys may think about that. Since it only have rotation part, right? Because all the body particles on AB will have a rotation around point A or axis A, right? So why is derivative equation still have three equations? Why? Because let me tell you. So let's see we have its mass center C, and we can, because this color is not good enough because you guys cannot see that clearly. Maybe I will change it into this. So we can, according to the direction of the alpha, can write as this. This is mass center is acceleration AC will have component ACT, right? Which equal alpha times FL, right? Can you guys understand this? We have learned this. I have repeated that many times. It also have another component. We call that ACN. That means it's a long, great set seal. I don't know how to read your name correctly. So number 18. So we also have another this ACN, right? ACN. So we know that actually another ACN component is will equal omega squared times FL. So since it has a rotation around the point A, so we can easily give this. So we will have GA, which is its mass moment inertia. It will be 1/3 ml squared. It should equal times alpha will equal MAF. So let's see, it also have M here. So the M is the reason why this bar AB have a fixed rotation, rotation around the fixed axis. So it will just equal because at this mass center it also have a gravitational force, right? So we can write this. So I just try to explain to you guys why we still have this equation. So let me change the color once again. I don't have many choices. So if we try to figure out what the magnitude of FAY and FAX is, FAX is, right? So we can use this. We can use this. Actually, we will have for simplify the expression. Let's see. I think not good because you cannot see that clearly. Let's see. This is theta, and we will have a P here. P is gravitational force. So I just try to explain to you guys why we still have give this a derivative function. So when we try to figure out the magnitude of FAX and FAY, so we will have M AX is equal sigma FX, right? It actually equal FAX. That's what we want to find its magnitude, right? And minus what? So we have because this in this example we will find because this P is totally along the vertical direction and M just a moment. So actually we find FAY is 0. It's 0. So I just try to tell you guys P should along this direction. And also we have MAY. MAY will equal sigma FY. So we will have FAX, FAY minus P. See? So if you can find the AX and AY, you can find FAY and FAX, right? So here we have ACT, we have ACN. So because we have this angle theta, so you can just use, because here we have A equal ACT, plus ACN, right? So we only need to project this equation onto x-axis and the y-axis respectively. We will find AX and AY. Then we can use this equation, that is 质心运动定理, the theorem of motion of center of mass, to find FAY and FAX. That's why for second, when a body have a rotation around fixed axis, we still have three equations, right? And the third one is a more generalized case. If the body have have a plane motion, then it clearly we have these two equations plus this. But this time we will not use GA, but we should use GC, because GC is more useful for plane motion, right? So that's the topic of this chapter, differential equations of motion of a rigid body. I hope you guys can have typically a basic understand of this thing. So since we still have some time, we'll try to see some example. Let's see the first example. This one is not very easy, so I hope you guys can understand. So let's see. A circular homogeneous field of mass m and radius r. So when I am so all the constant will change into Chinese, right? So when I read this sentence, I will stop here and ask a question. So here I will ask to you guys the same question. What means a homogeneous field with mass m and radius r to you? That means when you read this sentence, you must think about what there's something actually, let me put it in this way. That means the sentence will have some hint to you or some clue. It have some hint to you guys to help you to tackle the example, to tackle the problem. So I mean, if this wheel is a circular homogeneous with mass m and radius r, for me, I will immediately have this conclusion: is mass moment inertia about point O, or here should be its mass center point C, right? Will equal half m r squared, right? That is the hint. That's the true meaning for the sentence. So it tells the circular homogeneous field of mass m, and radius r is placed on a plane of inclination angle phi. That means this phi, this slope have intersect angle with horizontal line with angle phi, right? Under the action of gravity. So we have gravity mg along this vertical direction, and it starts to move. It starts to move. When the starts happen, it's from rest to move, right? That means the initial condition is how the system is on rest, it's stationary, right? So assuming that the coefficients of the static and the kinetic friction are F and F prime respectively. So can you guys still remember what means the coefficient of static and kinematic friction F and F prime respectively? I remember when we learned that chapter, friction chapter together, I only have the Chinese version of PPT file, right? Actually, some gentlemen from our WeChat group gave me the English version of that chapter. Do you guys still remember? So actually at that chapter, we have talked about static friction and kinematic friction. So for static friction, we have when the critical condition fulfilled, that means F max equal F Fn. That is Coulomb's law. We call that Coulomb 定律, right? So if the two bodies, that's this slope and this wheel, have a kinetic friction, that is static friction, that's the maximum value of static friction. We also have FF. This is kinetic friction. We should always equal F prime times Fn. And we also have the common sense that this FF will be a little bit lower or smaller than F max, right? And this equation only fulfilled at the critical point. That means it will have relative movement at that point. See, that's what we have learned. So some gentlemen said this chapter is the most difficult chapter we have learned until now. Why? Because we always talk about all the things we have learned. And a lot of things, although we have learned, but you guys have totally no idea what about what I'm talking about, right? Because you guys forget that totally, right? So that's why you guys feel it's very difficult. So we keep talk about all the knowledge points we have learned. So our time span is long enough. We have this is the fifth week. We have total 16 weeks, right? We have learned a lot of stuff. So what remains on your brain? What left? Maybe a lot of things we have mentioned and we have learned that you already forget totally, right? So it's okay. It happened to anybody, including me, right? How should we tackle this thing? We should back to the chapter, we should back to the textbook and review, right? Try to review what we have learned, then you will remember a lot of things. So, right? So neglecting the rolling resistance. We do not consider the rolling resistance. Analyze the motion of the wheel, right? Analyze the motion of the wheel. So we'll talk about a little bit. Actually, this is not easy to understand. So you guys see the solution together. So for convenient, we build another fixed coordinate system. Here O is origin point and its x direction actually is on the slope. And then is y just a vertical perpendicular to x. So maybe you guess just let me incline your head a little bit. Then we will have this, but its gravity also along the vertical line. It's independent to the direction of your coordinate system, right? You can select your coordinate direction arbitrarily, but you cannot change the direction of the gravity, right? And so the free body diagram we call FBD, and the motion analysis diagram, that is MAD, right, are shown in here. So for the force analysis from FBD, we have mg here, we have Fn along the normal line direction. We also have friction F. We just assume its direction along this direction. So we don't know what type of the friction force is. So we should discuss that. And because this wheel will will rotate. Actually, this wheel will have a plane motion, move from the high position of this slope to the lower position. So it maybe have some rotational part and the moving part. Let's see, it because the center C always have the fixed distance to the slope ground. So it will have AC, its direction will always parallel to this X direction, right? So we will have ACY will always equal 0 because our direction of coordinate system here. ACX always equal AC, right? That's the convenient for this direction of X and Y. And because the wheel is in plane motion, applying the differential equations of plane motion, we obtain, right? So we just give the, it is the plane motion, so we give these three equations. MAC, that direction actually is MACX, should equal sigma fx, so we have mg sine phi minus f, right? And another is along this y direction, so we have MAY, AY is 0, right? MACY is 0 equal, so mg cosine phi along the negative direction of f of y, so minus mg cosine phi plus f1. So you can find f1 along the positive direction of y. So we have this. And this one, maybe you guys have a little bit confusing of this. Actually, this I also used to express mass moment inertia. So you guys can think it should be this. So maybe 20 years ago, when I am a student at college, when I was learning this course, we just use this I to denote mass moment inertia. So that's okay, it's the same thing. So you guys can think about GC alpha equal FR. So that's the three differential equation of a plane motion body. So from the middle one, we have Fn will always equal mg times cosine, not theta, should be phi, right? Should be phi. Fn equal mg cosine phi. So what about this and this? We should do a discussion. So we should talk about that. But today we don't have enough time. Then we'll leave that, left that to next time. So I think it's all for today. Because the constant is very difficult, so we still have no homework for you guys. If there are homework, maybe that is a kind of advice. I hope you guys, I highly recommend that you guys can back to this chapter and read it by yourself again and try to understand the more the possible you can, right?
Ok,老师。
That's all for today. Next time we will review this example. We'll talk about its different conditions, right? So that's all for today. Bye bye for you guys. Bye bye.
拜拜，老师。拜拜，
下课吧。
老师。
再见，老师。
拜拜拜。
再见，老师。